Hi, hello everybody. So after studying sets and functions in last couple of classes, let us see what relations are today. Relations is basically a mathematical object. These relations have got n number of applications in computer science. One of the beautiful applications of this is the relational database management systems. You might heard about it. This relational database management systems has got its concepts derived from these relations only that we are going to talk today. When I say RDBMS, any famous databases that you know, be it Oracle, be it Sybase, be any famous databases you know, all of them, most of them are relational database management systems, and they have got their background or basics from the relations. They derive their mathematical background from this concept called relations. We will define what a relation is, and we will see when we will call a relation transitive, reflexive, symmetric, and then we will see what is an equivalence relation, what is a partially order on a relation, and we will see some operations on these relations. Like we have been seeing operations, we have seen propositional logic, we have seen on sets, we have seen on functions. Similarly, we see some operations on these relations and how they are directly applicable or how they have been directly taken into RDBMS. That is what we will see today. Basically, a relation has been defined as a binary relation from A to B, like this. If you have got two sets A to B, A and B, and you can take its Cartesian product. What a Cartesian product we have already seen, and a relation is nothing but a subset of this guy. A relation is nothing but a subset of A cross B. Any subset of A cross B will be a relation. In fact, it is a binary relation because there are two guys that on which you are talking about the relation, hence it is called binary relation. So in fact, the empty set is also a binary relation because empty set is subset of A cross B, hence it is also a relation. So any subset of A cross B is a relation. Then let us define some meaningful relations. Say if n is the set of natural numbers that is running from 0, say I include 0 in it, I define a relation like this: set of all A comma B belongs to n cross n such that A is less than B. This relation, is this a relation or not? First of all, yes, this is a relation because I am deriving the tuples from n cross n, hence this set I can call it as a relation. Am I taking all the tuples from n cross n? No, I am putting a condition, or probably I am putting a predicate. I am applying a predicate. That predicate is if the first guy in my tuple is less than the second guy, then I consider that the tuple to be in this relation, otherwise not. So the predicate that I am applying on all the tuples n cross n, or the relation that I am applying on all the tuples n cross n is if the A is less than B, then I put the tuple, otherwise I don't put the tuple. This is definitely a relation, and probably I would love to call it as less than relation. It's just a symbol. This is equivalent to saying set of all A comma B in n cross n such that A is less than B. This is a relation. I may call it as less than relation. So if you ask me 2 comma 3 is going to be there in this relation or not, I say yes, because 2 is less than 3. 4 comma 7 is going to be there in this relation or not? Yes, it is going to be there. 7 comma say 1 is going to be there in this relation or not? No, 7 comma 1 is not going to be in this relation, because 7 is not less than 1. That is how I define a relation basically. You can call it as A or B. That is how you are relating A and B by some meaningful relation. Having defined what a relation is, you can in fact think of n number of relations. If you have got set of all human beings as one set, and then you can think of n number of relations on this Cartesian product h comma h. You can see you can think of a relation by all the human beings, say x comma y belongs to my relation if x is married to y. This is a relation. This can afford to be a relation because basically this set is subset of the Cartesian product h cross h, and the relation that I am putting is if x marries to y, then I put this tuple here, otherwise I don't put this tuple here. So this is a relation. You can put likes, if x likes y, then that is another relation. You can think of n number of relations. Having defined what relation is, let us see what is complementary of a relation. Suppose I have got two sets A and B, and I have defined a relation called R on A and B. Then complementary of the relation is nothing but all the tuples that are not there in R defines complementary of the relation R. It is represented typically by this particular symbol. You put R and put a straight line over it, and basically it means that it contains all the tuples that are not there in R but are there in A cross B. You can define it like this: A cross B such that A comma B is not in the relation R. That is how you define it. It's complementary. All the guys who are not there in R are going to be there in R complement. If you see the less than relation that we have defined, let us see what is the complement of the less than relation that we have defined some time back. So if this is the complementary of the less than relation is going to be set of all tuples A comma B, set of all tuples A comma B that are there in n cross n, such that A comma B is not in this particular relation that is less than, isn't it? Set of all tuples in n cross n and which are not there in less than. This is what complement of less than. If you can write it nicely, you can write it like A comma B belongs to n cross n such that A is not less than B. This is what you write, and this is equivalently saying A comma B belongs to all n cross n such that A is greater than or equal to or equal to 0, A greater than or equal to B. Possibly you can say this, and the complement of less than relation now happens to be another relation, that is set of all tuples A comma B such that A is greater than or equal to B. Possibly you can call this relation by the nice name called greater than or equal to. So now you understand what complement of a relation is. You take the relation and consider all the tuples of A cross B which are not there in this particular relation. That is what a complementary of relation is. Having seen what a complementary relation, let us see inverse of a relation. If R is a relation on A cross B, then R inverse is going to be a relation on B cross A defined by this particular statement. R inverse is basically a relation that is acting on B cross A. That is how I am defining it. I will take all the tuples B comma A, all such tuples such that their reverse, I mean AB, if AB is in R, then I say BA is going to be in R inverse. It is quite intuitive. For a tuple to be in R inverse, for a tuple like BA to be in R inverse, the inverse of the tuple, that is A comma B, has to be there in R. That is how it is defined. And relation on a set, we have been seeing relation from set A to B. That is what we have been dealing with. How do you define relation on a set? It is very simple. If your relation happens to be on A and A itself, then you call this particular relation R on the set A. Relation R on a set A is nothing but R is a relation from A to A, then you call it. The relation that we have seen some time back, less than, is a relation on the set of natural numbers, isn't it? Because less than is a relation on n cross n. Here both n and n, both sets happens to be the same, hence we call less than is relation on a set n. So this less than is a relation on a set, and if you can define this particular relation IA such that A comma A belongs to A, then this particular relation is also you can call a relation on set A. Having defined relation on a set, we will see what is reflexivity means. You have got, say, R is a relation on set A, then I get to understand that R is basically a subset of Cartesian product A comma A. I call R a reflexive if A comma A belongs to R for all the elements of A. If this particular condition is satisfied, I say R a reflexive relation. R will definitely have lot more elements than A comma A alone, of course. I will say R a reflexive relation if for all elements of A comma A should be there in this particular relation R, then I say R a reflexive relation. Now let us consider this greater than or equal to relation. How you define this? How I am going to define this particular relation is set of all A comma B belongs to n cross n such that A is greater than or equal to B. This is how I am going to define this relation. Then the question is it reflexive or not? To check it, what I do is I will take any x in n natural numbers, then I have to prove that x comma x should be in greater than or equal to. Then I say that this particular relation is reflexive, otherwise not. I take any x, then for x comma x to be in this relation greater than or equal to x should be greater than or equal to x should be happening, then I can say that x comma x is in this relation. But it is very much true. You take any natural number, say 5 is greater than or equal to 5 is true. Any natural number for that matter, 525 is greater than or equal to 525. So you take any natural number that is going to be greater than or equal to that number. Hence this is going to be true for all the numbers in natural numbers. Hence I can say this guy is a reflexive relation, otherwise I cannot say. We will take another relation that we have been speaking. we will consider less than relation A comma B in n cross n such that A is less than B. This is another relation that we have been speaking. Can I say this relation is a reflexive? No, because you have got a number 5 in natural numbers, but 5 comma 5 is not in less than, isn't it? Why it is not in this particular relation? For it to be in this relation, 5 has to be strictly less than 5 because of this, because of the very definition how the relation has been defined. 5 has to be strictly less than 5, which is not true. Hence 5 comma 5 is not there in this relation, hence this is not a reflexive. That is how reflexive relation has been defined. Let us see what is irreflexive. I say R is irreflexive if and only if its complement written like this is reflexive. What I mean by this? For a relation R to be irreflexive, you know what its complementary is. Its complementary is, R's complement is, say R is working on A cross A. R is a relation that is working on A cross A, then R is a subset of A cross A, then R bar is simply the set A cross A minus R. Do you agree with this? This is what, how do you define a complement of a relation? Now for R to be irreflexive, this particular relation has to be reflexive. That means that for all the elements in A comma A should be in R complement. If this is happening, then I will call R irreflexive, otherwise not. We will do with an example. Let us take the less than relation. How is it defined? A comma B in n cross n such that A is less than B. This is how it is defined. Then what is the complementary of this relation? We have seen some time back that A set of all A comma B in n less than n, and what should I write? A should not be less than n. That is equivalently saying A should be greater than or equal to B. This is the complement of this particular relation. Now for this to be reflexive, this has to be reflexive. Is this reflexive or not? Yes, it is very much reflexive. You take any natural number x, then x is greater than or equal to x, hence x comma x is going to be there in this particular relation. X comma y is going to be there in the complementary of the less than relation, and this is true for all x. Hence we call this irreflexive because complementary of less than, that is greater than or equal to, is reflexive. We say a relation is symmetric. You have got, say, a relation on a set A, that means a relation is from A to A. Then I say this is symmetric if and only if I know that A comma B is in R, then it should be happening that B comma A should also be there in R. Then I say the relation R is reflexive, otherwise not. First we will see a relation which is not symmetric. We will consider our we will consider the same example that we have been seeing from some time, that is A comma B in n cross n such that A is less than B. This is a relation. Let us see it is symmetric or not. It is not symmetric because 3 comma 5 belongs to this relation and 5 comma 3 is not there in the relation. Do you say that, do you agree that 5 comma 3 is not there in this relation? Yes, it is not there because 5 is not less than 3. So now you have got a tuple which is there in a relation less than, and its inverse, that is 5 comma 3 is not there in the same relation. Hence we say this is not symmetric. For it to be symmetric, if A comma B is in the relation, then B comma A also should be in the same relation. Then I say that relation is symmetric, otherwise not. Less than is not a symmetric relation. Let us see another example. I will say H is set of all human beings. And then marriage is the relation that I am speaking here. Marriage is a relation that is working on H cross H. How I am defining marriage? Set of all x comma y in H cross H, where x and y happen to be human beings, such that x is married to y. This is the relation that I am talking. Is this a relation or not? First of all, yes, this is very much a relation because this marriage is definitely a subset of H cross H, because I am considering the tuples from H cross H only. Now is it symmetric or not? Yes, it is very much symmetric because if Rama is married to Sita, then you can always say that Sita is also married to Rama. If X is married to Y, then it obviously implies Y is married to X. So this particular relation is very much a symmetric relation. Whenever you say that X is married to Y, you always say that Y comma X is also there in the relation because Y is married to X as well. Hence this is a symmetric relation. Then we will define anti-symmetric relation. This is like if R is a relation on A cross B, A cross A, relation on a set A. So I say R is anti-symmetric if I know that A comma B is there if A comma B is there in the relation, then I should have this particular condition: B comma A should not be there in the relation R. If this is being satisfied for all tuples A comma B that are there in the relation, then I say this relation R is anti-symmetric, otherwise not. We will go back to our own example and see it. Less than relation, it is defined as A comma B in n comma n, A n cross n, such that A is less than B. This is the relation. Is this anti-symmetric or not? If somebody comes to me and say that, sir, P comma Q is there in this relation less than, then beyond a doubt I can always say that Q comma P is not there in this relation. Why? You know, if P is less than Q, then Q cannot be less than P, as simple as this. Hence if P comma Q belongs to less than relation, then I can always say Q comma P is not there in the relation less than. Hence this is less than will be is an anti-symmetric relation, and we will see when do you say a relation that is working on A cross A is transitive. I will say this relation is transitive if I know A comma B is in the relation and B comma C is in the relation R, then these two things should imply that A comma C is also there in the relation. If such a condition is happening for the relation R, then I say R is reflexive, otherwise not. For all the tuples such that A comma B and B comma C are there in the relation, then A comma C should also be there in the relation. If this particular condition is happening, then I say the relation is transitive, otherwise not. We will take a simple example and see it. We will take a simple example. Set of all human beings, H represents set of all human beings. Then R is a relation that is acting on H cross H. Then say if I am defining R like this, set of all x comma y that are there in H cross H, such that x is ancestor of y. Say I am defining a relation like this, x comma y, both of them are human beings. Then I put the tuple in R if and only if x is ancestor of y. This is definitely a relation, and this is transitive as well, because if somebody comes and says that sir A comma B is in R, then I get to understand A is ancestor of B, and somebody else comes and says that sir BC is also in R, then I get to understand B is ancestor of C. Then I have no hesitation in saying that A is ancestor of C, and hence it has to be there in R, and it is there in R very much. So if somebody comes and says me that A is ancestor of B and B is ancestor of C, then I can always say that A is ancestor of C. This I am able to say because the relation has been defined like that, and hence A comma C is going to be there in the relation R. Whenever these two properties are happening, I can definitely say A comma C is also going to be there in the relation R. Hence R is transitive. The way we have defined R here is a transitive relation. And say on the same domain, say I define a relation S on H cross H, again on the human beings, and I define S like that, like this, x comma y in H cross H, such that x likes y. This is very much a relation basically, because S is subset of H cross H. Is this a transitive relation? No, because if x likes y and y likes z, it does not mean x likes z. Hence S is not a transitive relation, and people call it as intransitive as well. Let us see this functionality. This is a little bit complex, let us understand it. Say R is a relation on A cross B, so R is definitely a subset of A cross B. It might have been defined and the way the guy want it to be. You can define relation like as you want it to be. And if you see, if I have got an element A and say B is having the set like B1, B2, B3, B4, say B is having say 4 elements inside it, then this relation may be having A comma B1 in it, A comma B2 in it, depending on how he has defined it. A comma B2, A comma B3 and A comma B4. It may have all of this or only few of them or none of them. When you define R, it is going to happen for a given A. And we are calling R is functional when there is at most one B such that A comma B is in R. In this case, I will call R functional only when only one of these things should be there in the relation, that is either A comma B1 or A comma B2 or A comma B3 or A comma B4. Only one of them should be there in R, or none of them should be there in R, or none of them can be there in R, and this should happen for all elements of A. When this particular condition is happening, I call R is functional, otherwise not. In fact, I will call R is functional with respect to A. Let us understand with an example. Let us define R. Say let us define a relation S. Set of real numbers cross set of real numbers, that means A comma B and real numbers, such that A plus B is equal to 0. This is definitely a relation, there is no doubt about it. Now what I am saying is, given any A in R, for that matter take R to be 4, how many B's, that means 4 is going to be paired up with how many real numbers, and it is going to be there in this relation. Just think, 4 can be paired possibly only with -4, and it cannot pair up with any other thing for it to be in the relation S. You understand this? 4 comma -4 can only be there in S. 4 cannot be paired up with any other real number, because that real number plus 4 cannot be 0, only 4 plus -4 is going to be 0. Hence, for a real number, there is only one guy that it can pair up with to be in the relation. Hence, this relation is called a functional relation. It cannot pair up with anybody else except one guy. It doesn't matter if it cannot pair up with any of the guys, that is also fine for it to be functional, but it cannot have more than one guy to be paired up with. That is what is functional means, and this should be happening for all the elements of R. Then I say that relation is functional. Hence, this can very much a functional relation. If you really have to understand it, less than, you think about the less than relation. How you define it? Less than relation is set of all A comma B in say n cross n such that A is less than B. Then you take the same 4. 4 can be paired up with 8, and it can be there in the less than relation. 4 is less than 8, so it can be there, and 4 can as well be paired up with 9, isn't it? Because 4 is less than 9, so 4 can be paired up with more than one guy in n. Hence, it is not functional. I hope it is clear. And another definition, we call R is anti-functional if the inverse relation is functional. And just like we define composite functions, we can define composite relations as well. If R is a relation from A to B and S is a relation from B to C, then you can define a composite relation S circle R such that A C is going to be there in the composite relation if there exists a B such that A is related to B and B is related to C. This is just the way that we have defined in functions. So by making use of this composite relation, you can in fact define Rn relation by compositing it recursively like this. R2 R for that matter R2 will be R circle R, and R cube will be R circle R, that is R square. Like that you can recursively do it. And we have been defining binary relations like this, or if two sets can be distinct, you can define these are all binary because there are two sets on which you are working on. You can talk relations on n sets as well. When you are talking relations on n sets, it is going to be simply this: R is subset of A1 cross A2 cross An. Then you say this is n-ary relation because there are R sets on which you are working on, and sets AI are called domains. So in this case possibly you say that you have got n domains of R, and the degree of R you say is n. So the functional definition in the similar way that we have defined for binary, we can extend it to the n-ary also, and we will see with this with an example. We will take a small example to see what we have been seeing with a case study. So say set S be the set of all student identity numbers for say 4 students. This S is set of all student ID numbers, and say n is the set of all student names. Then say C is the set of all CGPAs that they have got, and say F is the set of all first degrees that they are in, and say P is the set of all the specializations that their degree is in. Say if I got all these 5 distinct sets, then when I talk the Cartesian product will look like this: S cross N cross C cross F cross P, where S is the set of all student numbers, N is the set of all student names, C is the set of all CGPAs, and F is set of all first degrees, and say P is set of all specializations. This is a Cartesian product. Then definitely I can talk a relation on this Cartesian product, basically relation on all these 5 sets. I can define my own relation. So possibly I define a relation like this. I take a tuple here. If you really see it, how many tuples are going to be there? If I am not mistaken, it is 4 to the power of 5 tuples are going to be there. Then I consider a relation here of all those tuples. If a tuple corresponds to a student, I consider the tuple, otherwise I don't consider the tuple. That gives me a meaningful relation. The data about a student, I am saying that this Cartesian product is having huge data, because you are taking the Cartesian product of the huge data. I will put the relation. What the relation that I am going to put is, I consider a tuple only when it corresponds to a student. Then because I am considering 4 students data, I will get these 4 tuples, because all these things corresponds to a single student. This corresponds to one student, this corresponds to one student, this corresponds to one student. So only 4 tuples I will get. All other are meaningless data. If I really consider the Cartesian product, the tuple, there will be a tuple also in the Cartesian product of this, like this number and M Srinivas 7.25 BE honors and computer science. This tuple is also going to be there in this Cartesian product, but it doesn't really convey any message. I will put the relation that I will consider a tuple here only when it actually corresponds to a guy, a student. Then I will get 4 records here, 4 tuples over here. This is a relation. Why this is a relation? Basically these 4 tuples are definitely subset of this particular Cartesian product, and how I gathered is I put some relation there, I put some predicate there. Now let us see with reference to this particular ID number, is this relation a functional or not? For it to be functional, this guy should have only one row or one tuple in this particular relation. This particular ID number should have only one tuple in this particular relation. Yes, this guy is having only one tuple in this relation, this guy is having only one tuple in this relation, this number is having only one tuple in this relation, this number is having only one tuple in the relation. Hence we say this particular column or this particular student ID number is functional in the relation, in this whole relation. Why? Because this guy is actually pairing up with at max one guy, is pairing up with others only once. This guy is also pairing up with others only once. This guy is also pairing up with other data, I mean other data only once. This guy is pairing up other data only once. Hence this guy is functional. And if you really go back to, if you have studied database management systems, then such a guy is called a primary key, isn't it? A primary key of a table is like this. With that particular thing, it should be there only once. It should exist only once in the table, not more than once. I mean, if you say this is the primary key with this cell with this data element, you can have only one row, not more than one row, then you call it a primary key. Basically the concept of primary key has been derived from this mathematical concept, that is functional of the relation with respect to a set. Primary key is nothing but that. This is a primary key of this table because this particular set, that is student ID number set, is functional in this relation, in this whole relation. Hence you can call this a primary key, otherwise not. Now let us define what selection operator is. Basically it is an operator that we have been seeing. I mean, operators is not new to us. We have defined operators in propositional logic, we have defined operators in sets, we have defined operations in functions. Now we will see how we can define operators on the relations. We will take couple of operators. First we will take selection operator. Let us first do an example and then we will understand the concept behind it, and then we will actually see the formal definition of it. Definitely selection operator is something like this. This operator is operator when you apply it on any relation, then you get another relation. Definitely not the same, may not be the same. We will do it in example. Say this is a relation that I am having, the same relation that we have got it some time back. Then when I apply a selection operator, I will get the relation possibly with the same number of tuples, and some of the elements are going to be, some of the tuples are going of these are going to be here and some of them are not going to be here. How you define which elements are going to be in this and which are not going to be there in this is basically depending on the selection operator makes use is defined by means of a predicate. The selection operator is inbuilt with a predicate. I'll define a predicate and say I'll apply that predicate to this tuple, and if that predicate is satisfied, that means that when I put all these actual values into that predicate, and if I get a preposition whose truth value is true, I am going to put this guy here, otherwise I am not going to put that guy, this guy. So I apply this particular predicate to all these guys, and for whom it is satisfied I put those guys here, otherwise I don't put this guy here. So basically among all these 4 tuples, which one to select, which one not to select is decided by the predicate that I am defining. One has got all the flexibility to define the predicate as and she wants, as he and she wants. We let us do it with an example. So the predicate that possibly I am defining here in this example is CGPA greater than 8. That is the predicate that I am applying. So if predicate returns true, then I will put this guy in the new relation, in the resultant relation, otherwise I don't put this guy. So let us apply it to the first tuple. First tuple data is this, and here I will check is CGPA is greater than 8. CGPA is actually 8.26. So this predicate translates to the preposition, and preposition returns us true as its truth value, because the CGPA 8.26 is definitely greater than 8. Hence this particular tuple satisfies the predicate, and hence it is going to be there in the resultant relation. And similarly for the second guy, like for this guy, is predicate greater than 8, I apply the same predicate again, 7.25, which is not greater than 8. It is not satisfied, hence this guy is not going to be there in my resultant relation. It is not going to be there. For third, yes, definitely his CGPA is 9.31, so he is going to be there in my relation. For the fourth guy, yes, his CGPA is going to be 8, he is 8.5, so he is going to be there in my relation. So that is how I am applying my operator. I take each tuple here and I apply this particular predicate. If it returns true, I consider that in the resultant relation, otherwise not. Is this not an operator? I take this particular relation and I operate it, and I get a resultant relation. This is what is called selection operator, and exactly this selection operator has been exploited or made use of by all the RDBMS databases. In fact, SQL, when in SQL you can write, like when you write select student ID number, comma name, comma CGPA, comma first degree, comma specialization from, say, the table of name of this table is student, from student where CGPA is greater than 8.8, then exactly you get this particular table. This particular select has been exploited. This particular select has been actually derived from the selection operator that is working on relations. I hope this is clear, and this is how it is formally defined, selection operator. It gets too mathematical and it takes a while for us to understand it. If A is any n-ary domain, let A be any n-ary domain, and then you can define a predicate, and the operator works like this. In the operator, what it does is it applies predicate to each tuple, and if the resultant preposition gets truth as its true as its truth value, then you consider that guy, otherwise not. This is how the selection operator is being defined. Finally, we will see one more operator and see its relevance in relational database management systems. And say the projection operator, what it does is it is a say, if this is the relation that I am having, this is definitely a relation that is working on the sets S, N, C, F and S as we have defined in the last slide. So the projection operator is basically when you apply projection operator, you can always say that which sets or which columns you want to be in the resultant relation and which you don't want. Possibly you can define it like, boss, in the resultant relation I want only student ID number and CGPA, rest of the columns I don't need it, or rest of the sets I am not interested for now. Then this particular operator is defined like, go to this relation and take only the elements of student ID number and CGPA and put them in the resultant relation and don't consider any other data for this particular tuple. So this is how it is defined. Take only the student ID number and CGPA and ignore everything else. This is how it is defined. You can define a projection operator like this. You can have 100 columns, 100 coordinates under for your for in the relation. You have got 100 tuple relation. In that 100 tuple you can say that only 50 guys I am interested, other guys I am not interested in. You can project only those 50. Here in fact I am projecting student ID number and CGPA, not others. This is what this operator is doing for each. It goes to each guy and takes only student ID number and CGPA data, and it goes here and takes only this, and it goes here and takes only this. This is what a projection operator is, and this has got direct significance in your SQL structured query language. Like, you can always say this is the table that you have got. You can say that select student ID number comma CGPA from table student. When you say this is what is exactly happening, isn't it? So basically that particular SQL operation is being derived from this projection operator that is defined on the relation student. The mathematical background is from here. I hope we have understood couple of operators on relations and their relevance in relational database management systems, and we have seen what is transitive, what is symmetric and what is reflexive of a relation, and we have seen couple of examples for each of the cases. With this, let us conclude today's lecture and we will meet again. Thank you. Bye.